Yeah, good morning and welcome for the class. Still people are joining, maybe only 30 people are there now. So let us wait 1 or 2 minutes for others to join. So are you able to hear me? Mr. Muhammad Hamdan, are you able to hear me? Yeah. Okay, right. So, good morning and welcome to the class. So today uh, we will continue the discussion on internal forces, which we started in the last class, that means last week. So in this week, we try to complete this section, shear and moment diagrams. Shear and moment diagrams and relation between distributed load, shear and moment. So last class we have this internal loading, how the internal loading can be calculated. So this part is completed in the last class. So the other sections, like how to create shear and moment equations and diagrams. So we will learn those things in this class. So the objective for this chapter is to use this method of sections to determine the internal loadings at a point. So this is already being practiced in the last class, and I think you are able to do that by this time. And then now we see how to obtain the internal moment. We try to the representation in a graphical form, shear and moment diagrams in a graphical form. So this objective is at stake today's class. So we will try to achieve this objective at the end of this class. So let us see what is discussed in the last class, just for the recap of what we have in the previous class, so that if there is anyone not in the last class, he can understand what we are talking about. So this one is you see the beams, and these are the applications where we need to design a beam, and if you see the beams normally are not straight, they are tapered. So they are tapered because of a purpose. It is not for the aesthetic appeal. It is for some design aspect also. So these Y beams are tapered because it is to match with the internal forces and also to reduce the weight of the bridge. So this is the cause. So when you learn more about designs, solid mechanics and design of machine members and so on, then we will know. But the basic fundamental we learn from this class. So you see these fixed columns in the billboards, and they have some supports. To design also, you can see in the bottom they have larger diameter, and then as it goes, smaller diameter or a taper like thing. So you can see here the columns are thicker at the bottom than this one. So there is a purpose for that. Why don't we have a same diameter throughout this? It is with some purpose. So what is that purpose? Let us see. The purpose is the load moment that is coming onto the column. So in the other structure, this one also you can see it is propped by some additional frame that is to take care about the bending moment that is coming at that point onto the crane. So this is what we discussed in the last class. So any structural member, if we have a loading of some point load of 6 kilonewton and then a moment, then you can have reactions at the support, because this is a roller support. We have one reaction. It is also a pin. You should have both x and y directions, but x can be 0 later when you find. So when you want to know at a particular point what is the say for example at this point you take the section, so that section will have one reaction, the one which is here, and then the shear that is acting at the point B, and because you are cutting here there is a reaction that is there, so that reaction is normal reaction B and B. So this is how the free body look like when you cut a section along B. This method of sections we already practiced in case of trusses, so we are doing it here also. So the concept of section is not new for us. So when you take the section, the nomenclature here is the shear force is named as V. So when you take a big beam, and then in the big beam, if you take the section, at this section, you have a shear force that is V, and you have a reaction, normal reaction as you are cutting it here. So that is the normal reaction N, and you have the moment which is due to the external moment that are acting on it. So the bending moment. So whenever you cut a beam at a section, it exists, or there exists three types of loading. One is vertical shear force, and the other one is normal force, and the other one is bending moment. So this is the three components. These are the three components which can exist when you take a free body diagram of a beam. So when you say, as I said in the previous way, if you cut, there exists three loads, and next half, the left half also will have, right half also have three loads. So left half and right half you club, again nothing, you will get your own previous loading, because NA, NB cancelled out, VB cancelled out, MB cancelled out, so there won't be any load. If you that is why it is called internal load. That means the load that is experienced by the beam in the form of a stress. So this is the load that is coming onto the beam at any point. So this is what we want to know. So for example, in this beam with some length of say so many meters, we want to know stress here, stress here, stress here. So all the loading or the stress at each point is different. Maybe here it will have more stress, it will have more stress here, maybe less stress here. It depends on what is the load and what is the point of action. So actually, you know, the moment equation is force into distance. So as the d is changing, suppose you are taking a moment about this point, or for this load, you have to use this distance. So that is distance times the force. Whereas if you take the moment here, again the same force into same other distance, that is less distance. That means less moment acting on this point. So this is the criteria why we have more width at the bottom, beam more width at the starting point. All that is because as the distance goes on increasing, the moment goes on increasing. That means F into D. As the D increases, moment increases. F1 to D is increases. So the moment increases. To take care about the stresses, we provide more area to the beam wherever it is subjected to bending moment, more bending moment. So that is the reason. So this point anyway, we will learn in design and solid mechanics. Just an introductory part. I am just introducing the terms here. So with this, we have some steps established in the last class. Take an imaginary cut at the place where you would need to determine internal forces, then decide on the resulting section of the piece. Once you take an imaginary section, you draw the FBD, and once you draw the FBD, you try to solve it and analyze for N, V, and M. N is normal force, shear force, and moment. So this is the basic steps that are required to go for solution. So apply the equilibrium equations for the free body diagram to get your unknowns. So this is the example which we have solved last class. So I just quickly browse through it. So you take imaginary section. First point is take imaginary section. Before that, we want to know the reactions at A and B, so we can get the reactions by equilibrium equations. So easily you can do with the knowledge which we have now. And then you take the section at any point you want to do it. So the section is taken here C. So when that section is taken at C, what is the reactions is VC, normal force, and moment. So you have to find these things in order to estimate the. So to know that, what we require is equilibrium equations again. Equilibrium equations sigma Fx, sigma Fy, and moment about C. Moment about C will cancel out all these forces, and the only thing is 6 newtons into distance, that is 6 into 4.5, and MC. MC is actually should be in this direction. Sorry, in the other direction. So this is how we do it, and then we have solved this problem also. If you want to know the moment at this point and shear force at this point, obviously we draw the free body diagram and then take the section. So free body diagram of that will give you the reactions at A and B. After finding the reactions at A and B, we go for the section at which we want the moment. So the section is at C. So remember, you can take either of the left side. Suppose if you cut here, you can take the free body diagram of part 1 or part 2. Nothing wrong. Anything can be okay. So in this case, the left side is taken. So the left side part is A, and then it is having a reactions at 400 newtons and 96 newtons. And then we apply free body diagram, we get the required things. So example 3 also, I think we did this one also. This one again, the same pattern. You take a BD of section at C. So this time we take the moments about the A and C. That means this part is taken, A and C. So This is what we have in the previous class. So now we move to other section, that is shear force and bending moments. So to represent the forces, internal forces acting on the beams, and also the bending moment that is being applied or that is being subjected to the beams are subjected to, so that we wanted to represent in a graphical manner. So if you represent those things in a graphical manner, that is called shear force and bending moment diagram, shear force diagram and bending moment diagram. So two diagrams. So let us see how to do it. Before going to that, if any questions, we just take the questions and move on to next. So if there are no questions, so we continue with our lesson. So shear force and bending moment diagrams like this. So the actual design of a beam requires detailed knowledge of the variation of the internal force, means shear force, bending moment acting at each point of the axis of the beam. So in this regard, shear force and bending moment equations and diagrams are useful, because if you represent in a graphical manner, it will give you more idea which part of the beam is subjected to maximum stress, which part of the beam is subjected to maximum bending moment. So remember, a point at which more load is there is not the section at which more bending moment is applied on the beam. So it depends on the bending moment is related to the distance at which you are applying the load. At far, if it is at far, obviously the bending moment is more. So that is the bending moment is a variable of the distance. So these results are plotted, and if the load on the beam suddenly changes, then regions between each load must be selected to obtain each function. So let us see what is it meaning, because theoretically, if I make some statement, it may not be very clear. Only when you take an example, it will be very clear. So first, in this case also, to do this, we try to draw the shear equation, moment equation, and then try to plot it on a diagram. So let us see. So in general, the internal shear and bending moment functions will be discontinuous, or their slopes will be discontinuous at points where a distributed load changes or where concentrated forces or couple moments applied. So because of these functions must be determined each segment, the beam is located between any two discontinuous function loading. So what it means, let's say for example here, this is a beam with loaded, uniformly distributed load until a distance of A, and a point load P is applied at a distance of B. So if you consider the reactions, for example, if you take the section here, so, and let me take just for the easiness, suppose if you take the left portion, suppose if you take the left portion here, so the only reaction that is acting is this one. The reaction at the point is not named. Say, let me call it as reaction B. So this is, suppose if it is B, reaction B. So if you take the left section, it looks like you have some reaction V here, and some normal force here, and some moment opposing that. That is the big cuboid diagram. So what is this? What is this? This figure means? Sorry. What is this figure means is, suppose if you take the moment equation here, if you take the moment let me call this point as C, at C. So what is the upward force? Upward force is only RB. RB, if you take section also, here also RB. If you take section here also, if you take section at this point, it is RB only. At this point, it is RB only. At this point, it is RB only, because only force that is acting on the left side. So that is, say, if I write it in an equation, in the equation form, it can be written as V is equal to some function of V is equal to sigma So okay, better I use so V is equal to sigma that force, whatever reaction, say for example only it is RB. That means at any point between P to B, that is this distance, is only this distance is only the force that is acting is RB. If you represent that on a plane of paper, that means at point here, this is the final this is the point at which say B. So from B only R is existing. That means that is represented as a box. What is the magnitude of this is? Let me we will see the magnitude later. So whatever until from this point to this P, the only load that is acting on the left side of the right side of the beam is some R. So this is the magnitude of R. Why it is showing below, that is minus. So here we follow a convention, sign convention called any left side upward force, right side upward force is, right side upward is negative, left side upward is positive. That means we know normally on our convention upward is positive. Yes, upward is positive here also. Only that is holds good for left side of the, if you take the left side of the section. Right side of section should be opposite to the left side, because when you club they should get cancelled. So left side we follow the same convention what we have, that is upward force is positive, anti-clockwise moment is positive. So similarly here the net moment we will take here. Let us first do the shear force. Shear force is what? In other words, you can say if you take any section and you consider the right part, only force that is acting on the right side is R. So that is represented here. That means until here. Once you reach B, suppose once you reach this point, if you take section exactly at the point P, what happens is you need to consider P is acting downwards, which is, say for example, if I just take a section here. So when I take a section here, what and consider the right side, what are the forces acting? P is acting downwards, R is acting upwards. That means P minus R is the force. So P minus R is the net force that is acting here. This is the P minus R. That means the area that is the height that is shown here is equal to P minus R. So for example, just for clarity, let me assume R as 9 and P is equal to 12 kilonewtons. So therefore P minus R, that is 12 kilometers minus 9 kilometers, 3 kilonewtons. So on a scale this is 3, on a scale this is 9. minus 9 plus 3. And if you come to this point, at this point, until this point, okay, no changes. Until this point, what happens is upward 9, downward 12, therefore net 3. And then here, what happens if you take here, what happens? This will come. This will come as a function of x. Function of x. If you are at a distance of x from here, the load that is acting at this point is xa. So therefore, it is a proportional to the x until end. Suppose at the end, what happens? At the end, what happens is the net force is 9 kilonewton minus plus 12 kilonewton plus whatever ax. So ax is this. So all that is equal to. So this is a shear force diagram. Means what is shear force diagram is what is the net force? Suppose net force here is net force at this point is net force at this point is something say which is r minus p. Net force here is same, r minus p. Net force here is also same. Net force here is but also same exactly at b. After that, it keeps on coming. You can do the same thing from left side also. If you consider, as I said, you can consider the left side of the FBD. You take the section and take the left, whichever is convenient for us, we will take that and try to finish the problem. So similarly, moment equation. Moment equation also is represented in a graphical manner at this point. So what is the graphical manner is here. What is the moment equation in the section? Suppose here the moment equation is equal to, if there is a force of r, if you take the section here, r times x. So until that means r times x, rx is a linear variable. That is what is shown here. That is what is shown here. That is r times x. So x is equal to 0 at the x is equal to 0 point. Moment is 0. X is equal to 1. That is equal to r times 1. X is equal to 2, r times 2. X is equal to 3, r times 3, and so on until at this point. What happens at this point? You remember what is the scale is the horizontal scale is the length of the beam. Suppose length of the beam is 5 meters. So our horizontal axis is 5 meters. What it means is at 1 meter, what is the moment? At 2 meters, what is the moment? At B, what is the moment? At B, what happens? At B, if you consider this left side, right side, that is r times x. Okay, good. After this point, say here, after this point, say here, what is happening? R times x minus p minus x minus something. So that means the moment is not only anti-clockwise, there is a clockwise moment opposing it. So therefore, that's why it is reducing until what time? Until the other load is come into picture. Once the other load is come into picture, what happens? This is a parabolic, quadratic, because x into x by 2 is the moment. The moment that is created by ax is equal to a into x is the load here, and the load is acting at a distance of x by 2. That means ax into x by 2, that is ax square by 2. So here the load is increasing or decreasing in the form of x square by 2. So this is how we represent the net force on the beam in the form of a graph. But remaining equations are same. Equilibrium equation you take on the right side or left side. You take the free body diagram and you take the moment equation and shear force equation and try to see what is happening with x. So you can write an equation and keep on checking. Normally what we do is we try to identify at a salient point. Salient points means important points. Say for example B is 1, P is 1, at which it changes. Otherwise in between there nothing happen. In between it is straight only. Sometimes in between also not straight, where when there is a distributed load like thing. So it is constantly decreasing or constantly increasing. So to understand this is in a better manner, we take some example and try to solve some problem. Then you may get a good idea of what we are talking about. So any questions? So we go to the problem now. So in this case, let us see what is being asked. Draw the shear and moment diagrams for the beam shown here, PAB. So instead of PAB working with somewhat difficult, so let us assume some values. When P is equal to 30 kilonewton, so this is 30 kilonewton, and this span is 2 meters. This span is 4 meters. So that is given. Obviously, if you want to draw the shear and moment diagram, what is shear moment diagram? I just now I explained what is shear. Shear means what is the force, net force acting at each and every section. It keeps on varying. So for to do that, first thing is to draw the free body diagram of this whole structure, that means whole beam, and then find what are the reactions at A and B. So B is straight, A is also straight. Though we have one horizontal, it should be 0 because there is no horizontal force. So once you have RA, RB, you can find RA, what is AY, what is the force acting at this point. This is obtained by how you got 20, 30, 10? How you get the 20, 10? Equilibrium equation, sigma fx, sigma fy. So sigma fy you will not get directly because RA, say AY plus NB is equal to 30 kilonewton. That we know, but in order to solve it, you take moment about A, then that will give you RB into 6 is equal to 30 into 2. So therefore 30 into 2 by 6 will give you this is equal to 10. So that is how we do our calculation. Is it okay? So next thing is we want to see the free body diagram of a section, that means at this point or at this point. So you for drawing. So actually in order to draw, before I go, let me show you something here because it is available. I don't. So if you have a beam, so you must have something like. Wait. No, I am not able to. Okay, instead of this pen, better I use this cursor itself. So you have to draw, say for example, you have to consider the same length as you were to draw the moment shear force diagram. That means if this is your beam, say with suppose if this is your beam, and then you have to take the shear force bending moment diagram in the same width. Say for example, in this case, RA you find out RA is RB is 10 kilonewton, AY which is mentioned here, AY is equal to 20 kilonewton. So if you take the section at this point, what is the load that is acting on the left of it or right of it? Later we will see that. Left of it, what is happening? Only 20 kilonewton is working. So 20 kilonewton up is positive. That means your shear force diagram on this area is like this. So if it is shear force diagram, this is 20 and above. Similarly, up to after this point, what happens is 20 up, 30 down. That means net force is down. How much down net force? Net force is 10 down. Therefore, it will come like that. Let us see after solution. So here, if you take the section on the left side, so section on the left side here in the beam, it shows 20 Newton up, and the reaction here is V downwards and moment. So any zone which is less than 2 meters from the beam, what we have shown here, any zone which is less than 2 meters, that means from here to here, what happens is your 20 kilonewton up is the only force. So for example, if I take the left hand section, so that is what I am saying. So 20 kilonewton is the only force that is acting until what time? Until 2 meters. Once you reach 2 meters, then you take another section. If you take another section, it is not shown here because it is finished in a single step. That means left section and right section. So similarly, right section if you take, for example, right section if you take, and that means from here to the other end. That means here. If you take right section, what happens? Only force that is acting up on the upward is 10 kilonewton. That means 10 kilonewton upward. On the right side, what we said, 10 kilonewton upward means negative on the right side. So that is what is shown here. So on the left side, you go until where? Until here. So obviously it will be joined. You can also check in the other way. Other way is how, if you can check another section here, for example, a longer section, which means you have R 20 kilonewton acting here, that is 20, and somewhere here, this is, what is that? 10 kilonewton is acting, not 10, sorry, 30 kilonewton. 30 kilonewton. Therefore, the moment equation here is 30 kilonewton minus 20 kilonewton. So net force is minus 10 downward. That is what is shown here. So you can obtain shear force diagram very quickly. So is it clear what is this shear force diagram? Shear force diagram is nothing but net force acting on the beam at each point. That means on the whole beam here, now you can say in this zone, the force, shear force is minus 10. Similarly, the other zone in this similarly the other zone, this zone is now, we can say 20 kilonewton. Why this 20 kilonewton? Because if you see this figure, only force that is acting is 20 kilonewton until what time? Until x is equal to 2. When x is equal to 2, what happens? And x is equal to 2, another force 30 Newton is acting downwards. Therefore, you net force is 30 minus 10. Therefore, net force is 10, and that 10 is minus, because when you consider left side, downwards is negative. Or you can also check that with this other free body diagram, which you can also say 6 minus x. That means 10 kilonewton only upward force on the right side. As I said, it is we consider it as a minus, therefore it is shown minus, and then until it is constant. Until what time it is constant? Until it reaches 6. It reaches B. So that is the 4. So this is shear force diagram. So is it clear, the shear force diagram? What is it, the shear force? So shear force, if it is clear, Can anybody try to answer what is bending moment diagram? Bending moment diagram also similar. If you look at the diagram, it looks like a triangle. Why is it triangle? Huh? Why is it triangle? What is the magnitude at the peak? At the peak there is some magnitude. Moment, how moment can be solved? Similar moment equation. Take for the same free body diagram, take the moment equation sigma m for the free body 1, for example, left side. You name it as free body 1, free body 2, or part 1, part 2, like that, so that it will be easy. Suppose in the slide it is shown 0 to 6 meter, 0 to 2 meters. You need not mention like this, otherwise you just say part 1, part 2. So part 1, if you take the moment equation for part 1, what is the part 1 moment equation? Part 1 moment equation sigma m is equal to, or mx, we call it as mx1 is equal to 20 times x. That x depends on what is that? This x is equal to 0, it will be 0. At x is equal to 0, it is 0. At x is equal to 2, because at the 2 point another force is coming into picture. So x is equal to 2, it will be 20 times 2, that is equal to 40. Now it is decreasing. Why it is decreasing? You can check with the same equation. You can write after x, when x is equal to greater than 0, you can write moment equation like when x is equal to greater than 0. When x is equal to greater than 0, this mx is equal to, you can maintain the same free body. This mx will become 20 times x minus 20 times x minus p times, p is 30 times x minus 2. Okay. So when x is equal to 0, when x is equal to greater than 2, it should be x should not be 0 here in this case. X is equal to 3, for example. X is equal to 3, what happens? 20 times 3 is equal to 60 minus 30. 60 minus 30, how much? 30. So at x is equal to 3, the moment may be 30. If you want to know what is the moment here, I can say it is 30. So is it correct? Okay. Is it okay? Are you able to follow what I am saying? No sounds. Can somebody tell me at x is equal to 5? That means I want the moment at 1 meter from B. Moment at 1 meter from B. What is the moment at 1 meter from B? Can anybody tell me? You give me the answer here on the screen. When x is equal to 1 meter, what is the moment? Not x. I can say moment at point 1 meter from B. Moment at the point from 1 meter from B. What is the moment? What is the value of moment? One meter from B. Yeah, 10. Why 10? Because your reaction is, I don't know what is the reaction. Let me check what is the reaction. Your reaction is 10 here, and x is, I gave you 1 meter. So the x is, that means distance from 10 is 1. 10 into 1, 10. So similarly, if it is 2 meters, obviously, if it is 2 meters from B, what is the moment at a point 2 meters from B? If this is the question, normally this is the type of question. What is the moment acting at a point 2 meters from B? At a point 2 meters from B, what is the moment? Ayman can tell others. Can any other student can give me what is the moment at yes, 20. Yeah, if it is 2 meters, yes, 20. So this is what we say the moment diagram, bending moment diagram, and this one. So if you take a more complex, let us try to do this. So draw the shear force and bending moment diagrams for the beam shown in figure. So for this problem, at least you find AX, AY, BY. We will proceed further. So try to do AX, AY, BY and tell me what is AX, AY, BY. So before we draw shear force diagram for this, you must know reactions. So what is the value of the AX, AY? AX is 0, yes, good. AX is 0 because there is no horizontal force. Yes, AX is 0. So AY, BY, how do you get AY, BY? You can get by taking moments about one of the points, one of the edges, so that you get other one. AX is AY is 0. Yeah, suppose for this is the free body diagram. If you take the moment equation, sigma MA is equal to obviously BY times 4 meters is anti-clockwise, minus 800 times 1 meter, minus 600 times 3 meter, and 1200 Newton, because it's already moment, there is no distance, this is a moment. So therefore you get BY. Once you get BY, you can also use the same rule, sigma MY, or you can take the FY also, sigma FY also. Sigma FY is equal to 950 plus AY is equal to 1400. Therefore, 950 minus 1400 minus 950, you will get 450. So you can use either sigma FY also. If you want to solve this, you can write sigma FY also. So this part is over. Now you got all forces on your hand. So how to proceed? Shear force, moment diagrams. So shear force, let us say easy first shear force. Moment maybe you require to think a bit. Shear force only if you take very small part, say between, as I said, normally the shear force diagram you should project it from the beam itself. You have to draw a straight line. Sorry. So you have to draw a straight line just below the diagram like this, and then you try to project, say, until this part, for example, until this part, what is the force. So if you take the moment cutting here, that means section here. So what is the, if you consider the only left hand, what is the only force that is acting is AY. So AY is how much? AY is 450. So in this part, AY is upward. So shear force is very clear. Huh? So shear force diagram, it is 450 and it is upwards. Is there any doubt on that comment? So shear force, this is all shear force. Huh? This diagram. So the magnitude of shear force here is 450. Is it correct or any problems? AY. So next, if you take the moment here, cutting here, what happens? AY is upwards, which is 450 minus 800. So what is that? 350. Yeah? 350. So 350 upwards or downwards, you just tell me as per our convention. So this is the 350 minus 450 is positive. So you assume I have to actually I should give this diagram above that to give you a better idea. Let me at least do now. So it should be like this, huh? So now you understood in a better manner. So this at A, what is shear force? At A, if you take the cut here, only force that is acting is here is 450 upwards. Okay, so that is why this is 450 until 1 meter. After 1 meter, what happens if you take section here? AY minus 850, that is minus 350. So minus 350 is acting here. So until what time? Until it goes you have to check here because there is some another force, but that is moment, so it will not disturb anything. So after 3 meters also okay, but at 3 meters what happens is it is not as per scale. Just let me. Yeah, this should be like this, huh? So at you have to draw like this only. When you draw on a paper on an exam, you should show like this, because at A what is happening? At A what is happening? It is only minus 450. At B what is happening? What is happening is 800 newtons. Because it is adding 800 newtons here, it goes to minus, and it will be like that until this point. Or you can take a section here. Now you can check here. What is this? If you take the section here, what happens? Only force that is acting upwards is, what is that we calculated here? It is By is how much? By is 950. So the only force that is acting at this point is 950. So therefore 950 upwards. 950 upwards means 950 negative, because as I said, on the right side of the figure we take positive, I mean upwards as negative, therefore 950. So this is what is quantity here? This is 950. You got it? So shear force diagram is clear. What is that? You have one upward force, that is 950, therefore that is deflected here until what? Until 1 meter. After 1 meter what happens? If you take section here, 950 up minus 600, so therefore plus 350. I mean the 350 is the net. So from here it goes up here and then continue until what time? Until x is equal to 3 meter. So this is how the shear force. This is called shear diagram.
Sir.
Yeah.
Because the 950 Newton is outward, right?
Yes.
Why not is negative? Why is this not negative? Because the diagram is downward.
Yeah, this is negative. Yeah, 950 is negative because, as I said in the initial stage itself. So if you take the free body diagram of the right hand section, okay, RHS, right hand side, then upward force is termed as negative. If you take LHS, left hand side, then upward force is positive. You got it? So if you take this section and then consider the LHS, then upward force is positive. If you take the right section and because to make the what you call the uniformity in the sense, because when you if you take the right section upward positive, obviously if you take, suppose if you want to consider, in some books they say right hand side is positive, then left hand side should be negative. So
so we can we can opposite as a.
Yeah, opposite.
Okay.
You can if you follow opposite convention, like right hand side is positive up, left hand side up negative. The one point which you have to remember is you should not have upward right side or upward left side, both should be, cannot be positive, because it is a different convention, because you have to match it. Because when you take the right hand side, suppose as you said, if you say upwards is positive, okay, then you can draw 950 like this. But when you consider always 6 minus 6, so 950 minus what happens here, 600, that is 350. So you should draw like this. And when you come here, what happens, another adding another 800 means it will come down. So if you take the other convention, for example, by any chance or by, so your figure looks like this. Then you got my point. This green line also the other sign mentioned, okay, but both cannot be, both upwards cannot be positive. That means left side or right side, you have to follow either right hand rule or left hand rule. That's what.
Clear, sir. Thank you.
So you in some conventions this green color also okay. Only thing is you have to give. That's why when you see our slides or our textbook, they mention this. Why this mentioned? The actually sigma MA is enough. Why this is mentioned? Because what convention you are following? Your convention is plus is anti-clockwise, to make sure that this is given in that book. You need not write. Actually, when I am speaking sigma MA is 0, I don't mention this. This is mentioned because different people or different countries follow different thing. That is why. If you see here also sigma fx also, what does it mean? Positive when it is this direction. You got my point? Why this signal is given? So this is to make sure that everyone is follow on the. I mean, whoever is reading our book or slide to understand. Because you are correct. There are some books which are also drawing in this green like thing. That means positive left side downward. Okay. So if shear force is clear, we try to understand the moment. Here any question here? Let me check. By assumed only the by is negative. By is assumed negative means where is by? By is not negative. By is upwards. By is upwards because of any force that is say for example not only by. For example, here by is acting upwards. Right hand side upwards is negative in these diagrams. What we are right hand side upwards is negative. You can say, like, to be very specific, I can write like this: right hand side upwards negative. This is what I show you in this case. For example, in this case, I am saying this one, positive anti-clockwise, positive anti-clockwise, rightwards positive. Similarly, like that, upwards negative RHS. That means right hand side. When you consider right hand side part of it, that is what we followed in this case. Is it clear, Mr. Gabriel? So by is assumed negative means, yeah, that is the convention we following. So you can say, if you follow other convention, you write like that, LHS RHS negative. So that to make it clear, we are doing like that. So moment, coming to moment. So same convention we follow for moment. So for moment, if you see this figure for moment, what happens is, if you take the section here, moment on the right hand side is by times x. What is by? By is 950, yeah? By 950. So sigma m at section 1, let me call it as mx1, is equal to 950 times x. X is 0, 950 times 0, 0. X is equal to 1, 950 times 1, therefore 950. In between, how it varies? It varies as a straight line. Why? Because it is y is equal to mx. So therefore it's a straight line. So this part, I think everyone is clear. Huh? Is there any problem in this part? And one problem here is, because you see here it is positive again, we are writing it as positive because it is anti-clockwise. This convention is that what we follow so far. No, there is no problem. So right hand side anti-clockwise positive, which we already followed. There is no change in the our previous convention. So once you cross mx, say if you take section 2 at section, sorry, not we don't cut here. So if you take the section at 2, at 2 means here. So what happens is, sigma mx2, for example, mx2 is equal to 950 times x, whatever that x, minus 600 times, what is the 600 times what? Can anybody help me? 600 times what should I write there? $600 times what? No. 600 times x minus 2. X minus 2. X, because if you take x as a from b, if you consider x x from if you consider x from b, that x minus 1, because 1 meter less than that one. So 600 minus x minus 1. Is it okay? Yeah. 600 minus x minus 600 times x minus 1, not x, not 1 meter. X minus 1. X is, we don't know. If x is equal to 1, obviously that term is 0. Yes, then that is correct. Suppose in this case, as I said, in this case, x is equal to 600 x minus x minus 1, x minus 1, x minus 1, because let me write here, this is 950 times x is 1 minus 600 times x minus 1. Why? Because 1, because x is equal to, if you take section in here and this is called as x, this is x. Obviously 600 is 1 meter near to your section, so x minus 1. If x is equal to 1 by chance, it should be 0. Yes, it is 0, correct. And then you are left with 950 into 1. If you take up to until what time it is like this equation is valid. This equation is valid until 1200, until this point. Why? Because at that point another load is adding, therefore we should not carry it here. So we should stop at this point. What is at this point? What is the value of that moment? It shows 1300. Is it correct? How is it correct? Let us see. It is up to x is equal to maximum distance is 2 meters. So if x is equal to 2, what happens? 950 into 2 is 1900. 950 into 200, 1900 minus 600 times x minus 1. X is equal to 2 minus 1, so 600. 1900 minus 600 of how much? 1300. So is it clear? Why 1300 here? Is it clear? So if it is clear, then can you tell me on the other side? So we finish half of the moment diagram. So next half you can work out from the same direction or from the other direction. You can also work out from other direction, the moment. So that means for easiness, let me work out from other direction, but easier, because if you consider the right hand only, now the moments are adding. So for easiness, we can go for left hand portion. Suppose if I take the section in this case, as I said, to make my life easier, if I take section now here, what happens? Only force that is happening here is AY. AY is how much? AY is 450, it seems. So AY is 450. 450 times x. Until what time? Until 800. So 450 into 0 at here, increasing, and then at this point 450. Is it okay? And you take another section here and then consider the same section. If you want to avoid that thing, then what happens is 450 times x is minus 450 times x is minus plus 800 times x minus 1. Similar like this. What is that? AY times x minus 800 times x minus 1. Similar to this, you write another equation and you get this 100 or something like that. You check and tell me, is it correct or anything not matching to your calculation? Ah, 100. How to get 100? You just because if you substitute here at this point, what happens is, what is your at this point, what is happening? 1300. Suppose 1300 is the one which is obtaining only. You take the section of left or right. You get. But when you consider this point, you have to add 1200. When exactly at this point, if you see 1300 is what? 1300 is obtained from this portion which is positive, which means anti-clockwise. But at this point, what happens? If you look at this figure, the original figure says there is a 1200 Newton force acting, so moment acting at the point, this point, middle point. So that is what we have to add. So 1300 is the clockwise, anti-clockwise moment that is obtained due to the forces. But the moment applied is minus 1200, that is clockwise. So therefore net force is 100. So that is how 100 is obtained. That means from 1300 at the same point it will falls down to 100. Why? Because after reaching 1300, when you consider left side, right side, sorry, when you consider right side, it is 1300. But at the point there is a force acting at 1200. There is a moment acting at 1200, and it is opposite direction. So therefore 1300 minus 1200 gives you the net force. That is how we get 100. That is the answer to Mr. Who is asking? So, yeah, Mr. Roger, yes. So that is how we get. This 450 minus 800. Mr. Che, what is your doubt? 450 minus 800. 450 minus 800 is what? 450 minus 800. So 450 times, maybe his doubt also the same. Let us see from the left side point of view. So if I take just this figure is too clumsy, let me clear it out. So if you take the moments at this point, exactly at this point, and from left side. So what is that Mr. Cha is asking is, this is how much? This is AY. AY is 450. So 450 into 2 meters. So 900. 450 into 2 meters is 900 minus 800 times 1 meter. So 100. So 100 is the net. So obviously 100 is the what is shown in the figure. It jumps to 1300. How this 100 is acting in the clockwise, and 1200 is also acting in the clockwise. Therefore, it jumps to 100 to 300 like this. Is it clear, Mr. Che? 450 times into 2, you forgot to add, I think 452 times 200, 2 distance. 450 minus 800 is not the moment. 450 times 2 meter you forgot. That is why you got a different answer.
No, sir. Actually, the 450 minus 800 is the point of 100 that Roger asked. Yeah.
This point.
The point that Roger asked, the 100 one. He asked how to get the 100.
Yeah, 100. I told you, no, 100 is just now we displayed. 100 is very easy. 100 is just the point. You take the moments. For example, the one which I show here is you take the moment here. At this point exactly. So what is this vertical force? This vertical force is 450. 450. Yeah. 450 times 2. 450 times 2 is 900. Minus 800 into 1 meter. This is 1 meter. So 800. So that is how you get 100. But that 100 is when just before this point. But exactly at that point you have another plus 1200. Because this 1200 is the moment. There is no distance required for that. 1200. So that is how we get 100 jumping to. So that means actually this is a point of juncture where you just take a micron of 1200 before 1200, it is 100. Exactly at that point, it jumps to 100 to 1300. That is the what is called salient features, which we would like to know how it is the beam is behaving. Because the beam is subjected to why we are reading this subject or this this chapter is, so this is what, though it appears that the loads are acting on this body and it is subjected to loads, but if you see inside the internal stresses or internal forces, what happens, you can see visually, this is how the beam is stressed. That means from this figure, if you want to apply your knowledge to a next level, what is that we want to understand is, during this portion of the beam, it is subjected to one kind of load, let's say for example tension. Here it is compression, and means the load is net load is of different nature. One way it is tension, one way it is compression. Similarly, moments, the whole beam is not in the same. Some beam is subjected to a kind of a anti-clockwise moment with a less magnitude, whereas here it is subjected to maximum moment. So that is what it is, because it is 1200 added. So also it is slightly as goes on increasing. Now I answer your, can you answer my question? Can you now relate your the first diagram which I gave you, like why the beams are like this, say, when we say why beams are like this. Now you can you relate to why beams are like this? So if you see why like this, the load is not uniform, the bottom one is bigger, the top one is lesser. Can you answer now why is it so after seeing this this bending moment diagram? Of course, bending moment diagram for that also can be drawn, but can you guess what could be the reason? Or not, you not guess, you just you apply your what you call common sense now. So what is the reason? Reason of that being wider at the strength? Because if you now apply your knowledge now to that bending moment diagram, to that beam, then you can answer why. Because suppose in this case, if you see the slide that I show, so middle part is more subjected to more stress or more bending moment. So therefore we should provide more material or more area there. So in the case of beams also, in the case of the beams which I show in the bridge or in the columns which are wider, because the moment at the bottom, the moment that is acting at the bottom is more compared to the moment acting at the top of that billboard, because moment is force into distance. So force into distance is at the bottom distance of the whole pole, whereas in the middle it is not the whole pole. So that is why we want to reduce the weight, so we try to reduce the material at the top. Similarly in the beams, at the beam beginning, the load that is coming from the road is the distance times the load. So distance times the load is equal to moment. So near to the beams we apply more material. Away from the beams we apply less material. You can maintain a uniform beam, no problem. But if you maintain a uniform beam, extra material is wastage, that is optimization, all that comes into picture. So that is the reason, where there is no much requirement is there, we will try to reduce the weight by reducing the thickness of the billboard diameter at the top. Similarly, the road bridges, etc., they are tapered, because taper beam reduce the weight. At the same time, you should take care about the loads that is coming to onto the beam. So that is the reason. So now any more doubts? So if not, we try to do one more problem. This you may do on your own. Mostly try to do it on your own. Let us see how far you can proceed. So you try to answer this question. I think you are able to see now the diagram, which is here. Draw the shear force and bending moment diagram for the beam. So when a beam has a uniform load, something like that, your equation becomes somewhat difficult. it is not just like previous problem, because where you can moment is 800 times distance, 600 times distance, and reaction times distance, like that. Whereas the force here is a variable with the distance, so your equation becomes slightly complex. So another model. So try to do this. If you understand this, then the whole lot of shear moment diagrams, you understood everything. So for the FBD, I think no problem for each of you. Just try on your own the FBD and try to do something. I will. So you think of it. Let me take 2-3 minutes break. Meanwhile, you think and try to answer. I come back and finish the problem. So, welcome back. So let us see how to solve this problem. So this problem is having a distributed load which is 40 kilonewton per meter and 20 kilonewton at the end of the beam, overhanging beam. So A, B, you have reactions at A and B that you know very well. So we just proceed with a reaction here and another reaction at B. So that B action at B you can obtain by taking a moments about A. So moment about A can give you By times 8 plus minus into 320. How 320? 320 is 40 times the distance. 40 x is equal to how much? X is equal to 8 meters. So 40 times 8 is the load that is acting, which will be acting at the center because it is a center of gravity. So the replaced by 40 into 8, 320 is replaced and it is shown as a single force at the middle for the moment equation. So 320 times 4 and then minus 20 into 11, 8 plus 3, 11. So that is equal to that gives you, and 150 meter is 150 kilonewton meter is acting at the end of the beam. So it is having all kind of a load, one point load, one distributed load, and one moment load. So you get By, which is 206 in this case. Similarly, once you have By, you can take sigma Fy, which is equal to Ay plus 2065 minus 320 minus 20 is equal to 0. Therefore, Ay is equal to so much. I think Ay, By, everybody is convenient to know how is it and how to do it. So once you have done that, so what is that we can do? We can now take the moment equation, shear force equation first, sigma V, for a sigma V, maybe one part here or here, you can start here because this part is somewhat easy, not easy, because it is having a distributed load. You just to make yourself confident, you can take a shear force cut here, then consider this part. Can anybody tell me what is the shear force that is acting in this region, from this to this region? What is the shear force acting between B and the end point? Between B and the end point, that means between the 3 meters length. That 3 meters length, what is the shear force? Shear force is 20 kilonewton acting downwards. Acting downwards is positive in the right hand side. That's what we follow. So you can say shear force is 20 kilonewtons in this region. Is it correct? What I'm saying is correct or not? Is it correct or not? So anybody working? Everybody in the break, or have you joined or not? So no responses here. What is the shear force during the span of B and the end point, right side? And then if you are okay with that, next we go for second part, shear force, sigma V, V2, V3, like that. You may name it as I'm not writing here, you may name them as V1, sigma V1, sigma V2, sigma V3, like that. So in this case, So if you take the section here, the section is 20 kilonewton, and if you take section here, then your part comes as x into x by 2, something like that it will come. So are you working on it? Okay, Hamdan. Okay, right. So you try to find out at the salient features, and then I show you the final diagram. Let us see. Let me show you the final how it looks. But let us see how you get that one. So if this is your final diagram, I also let me take that first diagram. Yeah, nothing. I am just checking the diagram. It seems there is some problem. I just reconnect again, just do the problem. So hope you now can see the monitor. Is it okay now? Mr. Amir, are you able to see the screen now? Okay. So we continue our class now. So therefore, any solutions by anybody? So if you look at this, we already have the forces obtained, the reaction here, the reaction here. So the reaction at A is how much? A by 133, 206. Say this is say 134, 206. So if you take the section here, sigma V is equal to nothing but 20 kilonewton. What is that? That is acting downwards, which is positive in our case. So therefore, if you try to draw here, so it is something like 20 newtons, and then it goes until where? Until what? Until B. At B, what happens is at B, it is opposed by another force that is at 20 point how much? 206. So 206 is the force upward. So 206 minus 20, that is 186. Therefore, that is 186. So it will change to plus 22 minus 186 because the opposing force is here at the junction B. So after junction B, if you take the moment, sorry, if you take the section here, so what is sigma V at that section 2, that V2, otherwise V2 is equal to 20 downwards minus 206 upwards, my plus, because downwards is 1, plus what is this W, 40 times x, because this is x, if this distance is x, you can say 40 times x. And where is it acting? It doesn't, at this moment, shear force, no problem. So the equation is 40x. That means just to check whether we are doing it correct or not, x substitute 0. What happens? 20 minus 206, which what is the answer? Minus 186. So we are right. If x is equal to 0.1, 0.2, 3, 4 like that, you must see that when this is equal to 0 to know this 3.04. How I know this is 3.34? Distance. This is distance. What at what value of x is equal to this becomes 0. That way we should know the salient feature. This is called salient feature, where the shear force changes its sign. That means at this point it is negative, it changes its direction to the positive. Shear force is 0 at this point. So how do we know this point is? Equate this equation to 0. That means if this is equated to 0, what is the value of x? So you get x is equal to something. You just try this one. Is it correct? 3.34. So Just like that, x is equal to 1, it will have some value. X is equal to 2, it will have some value. X is equal to 3, obviously it will have some value. X is equal to 4, then it becomes a change of sign. So you see here, you may not be x what is, let me tell, somebody can tell me what is xc value? What is the x value? Calculate it and I want the x value. Why is so much time? Huh? Already equation is there, 20 minus 206, 4.65. So somebody says from Yang Kong, okay, yes, 4.65. But it is shown figure something else. What is 4.65 from which point? From 4.65 from B. 4.65 from B. 4.66 from B, maybe, as per this. So he is correct. 4.66 should be 66, maybe 6.56 something like that. Yes, 4.65 from B. The point which is shown on the figure says it is 3.34. 3.34 yeah, 34. What does it mean? It is 3.3 meter from the other end, not from this end. The one which we calculated x is 4.65 from B, 3.34 from other end A. Is it correct, Mr. Ya Kong Van Ivan? Okay. So anybody else got it? Mr. Che or Van or Kavinesh? Have you got the x value? X value is 4.65 according to Mr. Hong. Is it correct or wrong? So it seems nobody is working on it. So let me check the other points. Let us 4.65, yes, Shah, yes, 4.65 from B, B specific, 4.65 from B, because in the figure, if you see, it is showing 3.34. 3.34 is also correct, but from the other end. So what is shown here is that you got x is equal to 4.65 or 66 maybe. 65 or 66, whatever it is. So what is that means is you have an x which is changing its thing. That means somewhere here, somewhere here it is changing. So this is 4.65 from B. This is 4 point something, say 4.6. So this is the remaining one is 3.4. So total 8. This is varying with the velocity. Suppose if you want to know the other end also, you can check the section and then left and then check it. So where is it going on? So this is the shear force diagram. So why C force diagram is straight line from here to here? Why? How do we know? We know because it is straight line, because it is a variable of x, not x square. So variable of x means y is equal to mx plus c. This is in the form of mx, m is slope, x plus c. So mx plus c type, so therefore this is a straight line. That is how we know. And if you look now, come to the moment equation, sigma m, let me call it as m1 for the section 1 that is shown here, the same section. So what is the value of m? Can anybody tell me, help me to write the equation? 20 times x, 20 times x is clockwise. Clockwise means minus. Similarly, any other force is there, any other moment, minus 150. Is this correct? what I am writing here? Minus 150 minus 20 x is equal to the sigma moment equation about at section 1. Is that correct? Yes, correct. Next. So try to do the moment diagram. So moment diagram at x is equal to 0, what happens? At x is equal to 0, what happens? Minus 150 is the force. So that is what is shown here at x is equal to 0. When x is equal to this point, at this point, so when x is equal to at this point, 20 times x, that means 20 times 3, 6. X, and that means at x is equal to 3, your section 1 is finishes. X is equal to 3, what happens? Minus 60 and minus 150. What is that? Minus 60 plus minus 150 is equal to minus 60 minus 150 is 210. So that is what is shown here. And it is varying with x. Varying with x, that means this straight line. So how do we draw? Actually, you may have a doubt now. Actually, this one is we find out though I show here the final figure. Actually, when you plot on your own, how to proceed is, what we do is we write the equation what is shown here. So once you have once you have the points, salient points, what we do is we mark the salient points. Salient points means say O and O or B and the edge point. So at 1.1, what is the moment? So say 150, we say 150. And at B, what is then? Say 210. So this point to this point we join by free straight line. Next, from there, how to draw? This side we don't know for moment equation. So we want to know what is it. So we want to know what is it here from here. So therefore, what we do is at this point, what is the moment? Moment at this point is if you take the left section means so here in this figure, this left section means this side of it. So that one, if you take this left section here at this point, so RA times some value minus x into x by 2, 40x into x by 2. 40x is the distance. So if you write the moment equation for the left hand side, I think I will insert one more slide here. Explain. Suppose if we take the suppose now we take the left hand section here. So what is the sigma fx equation, sigma mx equation? Let me call it as say 3, section 3 is equal to, what is it? What is it is ay times x. X is the distance. By the way, what is x? X is the distance at which you take the moment equation. Ay times x is the anti-clockwise. Okay, anti-clockwise here is minus in this left hand side, plus 40 times 40 times x is the load, where it acts at x by 2 distance. So this is our equation on the left hand side. So if x is 0, what happens? X is 0, what happens? X is equal to 0, m is equal to 0. That is what is shown here. So at x is equal to 0, for example, if you substitute x is equal to 0 in this equation, so moment is 0, because 0, ay times 0 into 0, and x is equal to suppose 1 meter. Then ay times 1 plus 40 times 1 by 1 into 1 by 2, so that means 20. So whatever it is, what we want to know is there is one important point, that is where is the moment maximum, because until some time it is going maximum, later it will decrease. Why it is decreased later? Because later once you take the moment, this opposing force, because minus one is minus, another one is plus, so after some time this plus becomes more, therefore it will come down and matching to this point. So that is what we want to know. So we already know what is x is equal to at what point it is maximum. How do we know at what point it is maximum? We can know again in the case of sigma v is equal to 0, you can also make it try to work it out. But here we can use that previous point. That means there is one property called wherever there is a shear force 0, at that point the moment must be maximum. Therefore another salient point which we know is x is equal to 3.34. If you substitute in this equation x is equal to 3.34, you get your m max. M max is equal to, when x is equal to 3.34, so that will be 224. So that is how we know. And this point from 0 to 224, how it varies? It varies with the x square, means quadratic equation. Therefore that is why we show it on a parabolic equation. It's not a straight line. This is straight line. This is not straight line. Why this is not straight line? This is not straight line because it is varying with x square. So that is how we draw. Actually we mark silent features and then we connect them with a freehand sketch. So in the diagram, we mark first point A and next point, top point, what is there, and then where it is changes its direction, salient feature, and then we know where is it, and then we try to draw the figure, something like that. So it is not, we only find at silent points what is the, say here it is like this, and then from here to here it is the maximum. So from here to here out it is going, whether it is going as a this one, or what is it? It's a straight line. And then here from here to here, how it is going? It is going whether parabolic or straight line. It depends on what is our equation. We look at this equation, and based on this equation we try to join the salient features by freehand sketch with parabolic or, but what we have to know is we have to mark the salient features, like what is the maximum value, what is the zero value, where it changes direction. So these are the points which we have to mark. That is called the salient features of the moment diagram. So is it okay, or any doubts now? You can ask the doubts. How you get 40 into x? Yes, Mr. Shah, So 40 into x by 2 is are you able to see the screen now? Okay. So if you have distributed load, this distributed load is, for example, this is the area, this is the distributed load with x as the thing. So what is the load that is acting here? The resultant of this load is acting at the x by 2 and its magnitude is Wx. To give you more idea, just go back here. So here 40 Newton is the load. But when I say 40 into 8 is, what is that? 40 into 8 and means 40 into x. So 40 into x. Where is it acting? This is acting at x by 2 distance. X by 2. If I take x here, it is acting at x by 2. That is why the moment is, suppose if I take the moment of this 40 kilonewtons now, what is that? It says 40x times x by 2. That means if I convert into 8 meters, you know that 320 meters into 4. But if I am not converting into 8 meters, for example, if I say this is x, then what is it? 40 times x is the load. And where is it acting? X by 2 distance of the load. Because here the full span is taken, full span is 8 meters, therefore x is equal to 8 meters. That is how it is become 40 into 8. And where it is acting? It is acting at 4 meters from. Otherwise, if you don't know this variation, we say it is x in a generalized form. So therefore 40 into x. And if it is where it is acting at x by 2. So that is what we are doing here. So we are taking some section at x, say that looks like this. 40 is w into x. So wx. Where is it acting? It is acting at x by 2 from the end. Here it will act as x by 2. So therefore that is why we write 40 into x square by 2. 40 is the w here. So the generalized form for any uniform load is like that. Is it clear, Mr. Shah? 40 into x square by 2 is 40 is the w, x is the distance. X into x by 2, x square by 2 is how we got it is 40x is the load, x by 2 is the distance where it is acting. That is how, Mr. Shah. Anything else? So if you don't have any questions, we will stop because we are already at reaching our time. So we stop it here, and then if you have any question, you just ask. Okay, if no questions, then I think this is the last class for statics from me. Next week, Madam Norlin will take the class. So you join next Wednesday, Dr. Norlin's channel for the other topics. So the remaining 3 weeks she will take the statics class. So on the other note, I think all of you have gone through your exam 1 scores. It is already available in uLearn. You can review it, and if you have any problem or anything, you can ask Dr. Norlin or me. So I think hopefully you receive your exam 1 marks properly. If any, and for exam 2, because I may not be taking any statics class remaining 3 weeks, so let me give you some instruction on exam 2 also. Exam 2, You will have again 3 questions similar to 2 questions from the internal forces and the previous chapter trusses. Okay, so we will have 3 questions in the exam 2 also. So 2 questions from what I taught from last 3-4 weeks, that is shear force and bending moment diagrams, as well as the previous chapter trusses. So we have chapter number 5, 6, 7 for the exam 2, and also Dr. Norlin will add one more chapter, that she will they will tell you later. So 3 chapters from what I taught, that is chapter 5, 6, 7 for the exam 2. For the final exam, again maybe we discuss in week 12 because it's too early to, even if I say something you may forget. But exam final exam, don't expect normal questions like in the exam 2, exam 1. They will be a open-ended, some case study kind of a thing. So anyway, that we will discuss in the last week. Maybe Dr. Norlin or myself will give you some idea about final exam. So for exam 2, chapter 5, 6, 7 and chapter that is to be delivered by Dr. Norlin next week. So that is for exam 2. And regarding the assignment, I think all of you have uploaded assignment 2. I already downloaded. So maybe the scores will be posted sometime next week for the assignment. Quiz also, you know already what is your scores. So next week maybe I give you one more quiz in chapter 6 and chapter 7 in ULearn. You can I will post a mail so you can check it. So that's all from me. So we will have one quiz next week sometime. Maybe I will announce through mail that date and time in which the quiz is open. So upcoming weeks, statics, I think the madam will take the classes. So if you have any doubts, you can ask on this exams, assignments, etc. Okay, if you don't have any doubts, okay, thank you. And one more thing is you must answer your SSRT when it is asked, because last time statics you did not answer in my name. So next time, when next week or so, you will receive an SSRT, that means reflection tool. That student self-reflection tool, if you answer statics in my name also, because last time you never answered, and also I never asked you to answer also. So but next time you must include my name as a teacher for statics and then answer your feedback on SSRT. Okay. So though we will not miss Mr. Amir. We will meet in manufacturing anyway. Okay. Hope you are in even manufacturing also. Okay, right. That's all. Anyway, we still meet for manufacturing class next week also, and on the upcoming weeks also. Right. So you please answer your SSRT when it is required. And also you give your feedback on the poll in ULearn. Okay. Okay, see you maybe last week in the statics class. Okay, bye.